which is a lot, just really a lot of formulas, filling them in. Right to you. So the last thing we have to do is percent yield. So once again, not any new stoichiometry, just adding kind of another application to it. So when we write an equation out to represent a chemical reaction, that tells us what should happen in the reaction. But it's not what, oftentimes it's not actually what will happen. Sometimes the reactions do not make all of the product that we predicted it should based off of a stoichiometry calculation. And some of the reasons are that many reactions do not completely use up the limiting reactant. Maybe there's not enough energy for that to occur. Maybe the particles are not oriented the right way, but for some reason, not all the limiting reactant gets used up. A lot of reactions are somewhat reversible. So that means when the product starts building up, then it's going to reverse and go back to the reactant. Most reactions will have to be purified to get the product, and that can be difficult to do, or there might be some side reactions that are going on. And then reactants or products can be leaked or spilled, or they may not always be 100% pure. So that's kind of a human error situation. And then some reactions occur very slowly, and they're so slow that they stop before all the products are formed. So for any of those reasons, in a lab or in a real life setting, usually there is less of the product produced than what the calculation tells you should be produced. And that's what we're looking at today, the kind of the ratio and percent ratio of those two. So your theoretical yield is the expected amount of product from a reaction. So it's the answer to your stoichiometry problems. And it's the best case scenario if everything was perfect and nothing goes wrong. So this one is your calculated amount. And then our actual yield is the actual amount that is produced in a reaction. So it can be only determined in the lab, and it's what is actually made. So you're going to be looking at for words like produced or formed or isolated, something like that, that's going to tell you the actual amount, because the actual amount is given in the problem. And usually your actual amount is less than your theoretical amount. So to look at the percent yield, we're looking at the ratio relating the actual yield reaction to the theoretical yield. And that's going to be our little formula right there. The higher the percent yield, the more profit, so the better it is for companies. So to get our percent yield, we're going to take our actual yield, and that would be the given, divided by the theoretical yield, which would be your calculated amount, and then multiply it by 100 because we want it in percent. Percent yield should be less than or equal to 100. If you get a number over 100, then you probably have switched these two. So you need to go back and double check those. Sometimes when we do a lab, we may get over 100% because we don't do labs every day. We're probably leaving some impurity or water. But as far as your calculations, the things that you see on the test or quiz, you should always get probably less than 100%, but not anything over 100%. All right, so let's just look at a few of these. So zinc citrate is an ingredient in toothpaste that stops the growth of dental plaque by inhibiting their metabolism. If 6 moles of zinc oxide reacts with 10 moles of this hydrocarbon. Then calculate the percent yield if 990 grams of zinc citrate is actually collected from the reaction. So that's my product I'm interested in, and it says that there was actually 990 grams collected. So that's going to be my actual. That's what's given to you in the problem. Now, besides being a percent yield problem, what else, other kind of problem is this when I have two givens and they're both reactants? Yeah, a limiting reactant problem. So we're going to have to still do 2 stoichiometry calculations on this. And then once we get that answer, we'll use it to do our percent yield. So one of them is I have 6 moles of zinc oxide. And I need to get to grams of zinc citrate. Because that's 990 grams of zinc citrate. So I need to be able to compare those. And then my other one, I have still getting to grams of zinc citrate. And on this one, I have 10 moles of the hydrocarbon. All righty, so first thing we got to do is we got to find out the smaller amount. So I'm just going to follow my units. If I'm moles of zinc oxide, I have to be moles of zinc oxide down here. So this is where I'm going to use my mole to mole ratio. So for zinc oxide, it's 3. And for my product, there's just 1 mole. And then I follow my units, moles of zinc citrate. I'm going to be moles of zinc citrate down here. I do see grams, so I'd have to have a molar mass here. And that is 574.39 grams. So when I do that calculation, I end up getting 1,148, but I need to adjust for 3 sig figs, so it becomes 1,150 grams. So that's one of my answers. And then I have to do that for my other one. So moles of the hydrocarbon. So I have to have moles of this hydrocarbon down here. So coefficient of 2. My product's the same, so I start repeating everything. Zinc citrate. And then here's my grams. So I would need this molar mass again. 9 grams per 1 mole. All right, so that part you're ready to put in your calculator. I think you'll get something like that, but once again, I'm going to adjust it for my sig figs. All right, so those are my 2 numbers. So I'm always going to go with my smaller number. So that's my 1,150. That is my theoretical. It's a smaller amount, so that means that's how much would be produced. So to do my last calculation to get to the percent yield, I'm going to take my actual, which we said was the 990, divided by what I calculated the theoretical to be, and multiply it by 100. And at this point, because that 990 is just 2 sig figs, I want my answer to just have 2 sig figs. So you should get 86%. So you can kind of think of percent as being your units for percent yield. That's a pretty decent percent yield. Of course, if it's an industry when they're trying to make money, they want that to be as close to 100 as possible. All right, does anybody have any questions on that one? Where we got any of the numbers from? So that's a really long one because it was limiting reactant. So I had to do 2 stoichiometry problems. So that made it longer. Yes, ma'am. Oh, it's supposed to be 1.
Oh,
Sorry. Yeah, wherever I have my molar mass, it'll always be 1. All right. So at the top, this one is actually a real nice, easy one. All right, it says if in my equation, all nice and balanced. So it says if 2.5 grams of copper chloride was actually produced, so that's my actual yield. 12. But 25.4 grams of copper chloride was calculated as my theoretical yield. All right, so on this one, I don't have to do a stoichiometry calculation. It's given to me. So I just need to take my actual divided by my theoretical. Oops. 5.4 grams and multiply by 100. And I would want 3 sig figs. So what do we get for that one? 49.2%. So limiting reactant can be a really long percent yield. This one, because I'm already given my theoretical, I don't have to get do the calculation to get there. This is a really nice short one. All right, we'll look at one more that's in between. Kind of get it set up for y'all, and then y'all can work through it. Once again, I double check my equation is all nice and balanced. So it says a chemistry student uses 25 grams of lithium sulfate. So that's one of my reactants to react with excess barium nitrate. Remember, if something is in excess, that's just telling you that it's not going to be a limiting reactant problem. The student isolates 43.5 grams of barium sulfate. So this is my actual. It isolates. That was a word that the note said to look out for. Find the percent yield. So I have my actual, so I need to calculate my theoretical. And I'm going from grams of lithium sulfate to grams of barium sulfate so I can compare them. So it's going to be a 4-step problem. All right, I'm going to let y'all work through it. I'm going to give you the 2 molar masses you need. So that saves a little bit. Oh, 9.95 grams per 1 mole. And the other one is barium sulfate. 233.40 grams per 1 mole. All right, so there's your 2 molar masses. See if you can work through the problem. And when you get your answer, that'll be theoretical. So then you can do that last percent calculation. So what did you, somebody get a number for percent yield? 80, I think this year, you're only off on sig figs, 81.9. Because both of these were 3, so your answer, that other one we did was 2, but this one can have 3. So when you did your calculation here, you should have gotten 53.1 grams, and that is your theoretical. So to finish it out, I'm gonna take my actual, divide it by my theoretical, and multiply by my 100. That should get my answer there for my percent yield. Anybody have any questions on that one? All right, this number 3, we're not going to look at that. It's kind of a messed up problem. There's like a couple of big typos in it. So y'all got a little bit of time to look over your practice, which is what you picked up today. That's your percent yield practice. So y'all can work on that. If you have any questions, then let me know. If somebody else has the same question. Yes, ma'am. It will be, you'll have 2 givens and they're both reactant. So that tells you it's a limiting reactant problem. Yeah. Let me start recording this real quickly. I'm sorry. Just because they probably